Welcome to the lecture on inventory theory. This lecture is for chapter 5 of our course Operations Research. Inventory theory is concerned with the design of production systems or inventory systems so that inventory is available whenever needed and at the same time the associated total cost is minimized. It studies decisions of firms in connection with manufacturing, warehousing, supply chains, spare parts allocations, and so on. Inventory control problem is the problem faced by firms which must decide how much to order and when to order in order to satisfy their customers' need and at the same time minimize cost. Several deterministic and stochastic inventory models will be developed in this chapter. The whole content of this chapter will be covered in 5 modules. So, let us now start module 1 of this chapter, that is module 1 of chapter 5. In this module, you will understand the basic concept of inventory, why inventories are carried by organizations. You will know some terminologies, some costs which are associated with inventories, what is an economic order quantity or EOQ, and finally, some simple EOQ models without shortages. Let me start by defining what is inventory. The word inventory means simply a stock of idle resources of any kind having an economic value. Literally, the word inventory means a physical stock of goods which is kept in hand for smooth and efficient running of an organization. Inventory or stock of goods are kept mainly in the following 3 forms. Raw material inventory. It is the raw materials which are kept in stock for using in production of goods. Work in process inventory. It is the semi-finished goods which are stored during production process. Finished good inventory which wait for shipping or sale. Now, let me define why inventory is carried by organizations. Inventories are carried because of the following major reasons. To improve customer service, a suitable inventory policy helps to respond individual customers or organizations' request for products and services. To reduce costs, inventory holding costs are expenses that are incurred for storage of items. However, holding inventory items in the warehouse can indirectly reduce operating costs such as loss of goodwill, lost sale due to shortage, and so on. For maintenance of operational capabilities, inventories of raw materials and semi-finished goods act as buffer between successive production stages so that downtime in one stage does not affect the entire production process. To protect against irregular supply and demand, inventories provide protection against irregular supply and demand. An unexpected change in production and delivery schedule of a product can adversely affect operating cost and customer service level. To take advantage of quantity discount, we all know that large size orders help us to take advantage of price quantity discount. However, such an advantage must keep a balance between the storage cost and costs due to deterioration, damage, insurance, and so on. To avoid stockouts or shortages, consider the situation like labor strikes, natural disasters, delays in supplies, and so on. In such a case, inventories act as buffer against stockouts. Now, let us define some costs associated with inventories. First is purchase or production cost. It is the cost at which an item is purchased or produced. Carrying or holding cost. The cost associated with maintaining inventory is known as holding cost. It includes handling cost, maintenance cost, depreciation, insurance, warehouse rent, taxes, etc. Shortage or stockout cost. It is the cost which arises due to running out of stock. It includes the cost of production stoppage, loss of goodwill, loss of profitability, special orders at higher price, overtime or idle time payment, loss of opportunity to sell, etc. Ordering or replenishment or setup cost. The cost incurred in replenishing the inventory is known as ordering cost. It includes all the costs relating to administration, transportation, receiving and inspection of goods, processing payments, etc. Variables in inventory problem. There are mainly two variables, controlled variables and uncontrolled variables. Controlled variables are how much to order and when to order, and uncontrolled variables are holding cost, shortage cost, ordering cost or setup costs. Now, we come to define some terminologies which are usually used in inventory theory. First is demand. It is an effective desire which is related to particular time, price or quantity. Demand pattern of a commodity may be either deterministic or probabilistic. In case of deterministic demand, the quantities needed in future are known with certainty. Again, deterministic demand can be of two types, static and dynamic. Static means it is fixed and dynamic means the demand varies from time to time. On the other hand, probabilistic demand is uncertain over a certain period of time, but its pattern can be described by a known probability distribution. Ordering cycle. An ordering cycle is defined as the time period between two successive replenishments. The order may be placed based on two types of inventory systems, continuous review inventory system and periodic review inventory system. In continuous review inventory system, the inventory level is monitored continuously until a specified point known as reorder level or reorder point is reached. Whereas the periodic review system, the orders are placed at equally spaced interval of time. Planning period. The time horizon which the inventory level is to be controlled, over which the inventory level is to be controlled or over which the inventory system is considered is called planning period. Planning period may be of two types, finite planning period or infinite planning period. Lead time or delivery lag. The time gap between the moment of placing an order and actually receiving it is referred to as lead time. Lead time may be deterministic or probabilistic. Buffer or safety stock. To absorb the variation in demand and supply, sometimes some extra stock is kept in inventory. This extra stock is known as buffer stock or safety stock. Reorder level. The level between maximum or minimum stocks at which purchasing activity must start for replenishment is known as reorder level. Let us now define a very important concept in inventory theory, which is known as economic order quantity or EOQ. The concept of economic order quantity was first developed by F. Harris in 1916. The concept is as follows. Management of inventory is confronted with a set of opposing costs, that is holding cost and ordering cost. From the figure, it is to be noted that as the lot size increases, the holding cost increases, and when the lot size increases, the ordering cost decreases exponentially. On the other hand, if the lot size decreases, then inventory holding cost decreases, whereas the ordering cost increases. Thus, when we have to make a balance between these two costs in order to minimize the total cost. The figure shows that when the ordering cost and holding cost are equal, then the total cost is minimum. So, economic order quantity is that size of order which minimizes the average total cost of carrying inventory and ordering under the assumed condition of certainty, and the total demand during a given period of time is known. Until now, we have discussed the meaning of inventory, reasons for carrying inventory, the cost associated with inventories, and the basic concept of economic order quantity. We now proceed to develop some simple deterministic inventory models, and also we will find optimal decisions in each model. Before we go to develop inventory model, let us define some symbols which are used in connection with the inventory models presented in this chapter. C is the purchased or manufacturing cost of an item. C1 is the holding cost per unit time. C2 is the shortage cost per unit time. C3 is the ordering cost or setup cost per order or per setup. Capital R is the demand rate, and capital P is the production rate. Usually, it is assumed that production rate is greater than the demand rate. T is the scheduling period, which is a variable, and TP is the prescribed scheduling period. D is the total demand or annual demand. Q is the lot size or order size, and L is the lead time. We assume X as the random demand and Fx as the probability density function of demand X, and Z is the order level. Now, we develop the first model, that is model 1A, which is EOQ model without shortage. This is a deterministic inventory model. The assumptions of the model are as follows. We assume that the demand rate R is known and constant. The lead time is 0 or a known constant. Replenishment rate is infinite, that is, replenishments are instantaneous, or replenishment time is 0. Shortages are not permitted. Inventory holding cost C1, holding cost is C1 per unit time, and ordering cost is C3 per order. So, this figure shows inventory time diagram, and this diagram is drawn considering lead time as known, not 0. So, initially the inventory level is Q at time 0, and since the demand is constant, inventory level decreases, and ultimately it is reduced to some level what is called the order level, and where the order for the next replacement is made, and then inventory level comes down to 0, and by the time the next order is reached. So, the same cycle is repeated over time again and again. The average total cost of inventory system is given by Cq equal to half C1q plus C3R by Q. Since the minimum average total cost occurs at a point where average ordering cost and average inventory carrying cost are equal, therefore, we can write half C1q equal to C3R by Q, and which gives the optimal order quantity Q star equal to root over 2 C3R by C1. This formula was developed by F. Harris, and also this formula is developed by R. H. Wilson at about the same time. That is why the formula is called Harris-Wilson square root formula, and the model is called Harris-Wilson model. Now, some characteristics of model 1A. The optimum order interval T star can be obtained as Q star by R, which is root over 2 C3 by C1 R, and the minimum average total cost C minimum is equal to root over 2 C1 C3 into R. Now, if in model 1A the ordering cost instead of being fixed is equal to C3 plus KQ, where K is the ordering cost per unit item ordered, then there will be no change in the optimal order quantity. The ordering cost is assumed in such a way that a fixed cost plus a cost varies with the size of the order. That is why it is taken as C3 plus K into Q. So, if we assume such an ordering cost, then the optimum order quantity Q star will remain unchanged, because the average inventory cost in this case is half C1Q plus C3R by Q plus KR. K and R both are constant, so it does not have any effect on the optimal lot size Q star. Let us take an example. A manufacturing company purchases 9,000 parts of a machine for its annual requirements, ordering 1 month uses at a time. Each part costs ₹20. The ordering cost per order is ₹15, and the carrying charges are 15% of the average inventory per year. Suggest a more economic purchasing policy for the company. How much would it save the company per year? That means, if the company uses the normal way, that is ordering every month, and if the company uses the economic order quantity policy, then what will be the difference that we want to see here. Given that R equal to 9,000 parts per year and C1 is equal to 15 by 100 into 20, that is equal to ₹3 per part per year, and C3 is equal to ₹15 per order. So, using this data we can find Q star equal to root over 2 C3R by C1, which is equal to 300 units, and T star equal to Q star by R, which is equal to 1 by 30 year, that is approximately 12 days. So, that means that if the company uses the optimum order level policy, optimum order quantity policy, then he must order 300 units every 12 days in time interval. Now, in that case the minimum cost will be ₹900, and now if the company follows the policy of ordering every month, then the lot size of inventory each month will be Q equal to 9,000 by 12, which is equal to 750 parts, and annual storage cost will be equal to C1 into half Q, that is equal to ₹1,125. Annual ordering cost will be 15 into 12, which is equal to ₹180, and the total cost per year then becomes 1,305. Therefore, the company should purchase 300 parts at time intervals 12, because it gives the minimum cost, and in this case the cost saving will be ₹405. Now, we extend the model for the case of discrete units. So, if the lot size in discrete units, then this formula which we have already derived cannot be used for find the optimal solution. So, in that case if we assume that the lot size Q is constrained to values U, 2U, 3U and so on, then the necessary conditions for optimum of Q, that is Q star, are C q star is less than equal to C q star plus u, and C q star is less than equal to C q star minus u. From equations 4 and 5, if we simplify, then we get a relation in this form which is given in 6. That means we can find the optimal order quantity by satisfying the relation 6. Let us take an example. Demand in an inventory system is at a constant and uniform rate of 2400 kg per year. The carrying cost is ₹5 per kg per year and no shortage is allowed. The replenishment cost is ₹22 per order. The lot size can only be in 100 kg units. What is the optimal lot size of the system? So, in order to solve this problem, we see that demand rate R equal to 2400 kg per year, C1 equal to ₹5 per kg per year, and the ordering cost C3 equal to ₹22 per order. Here U is equal to 100 kg. Then if we use the relation 6, then the optimal value of Q can be obtained by trial and error method as 200 kg. Let us now study the sensitivity of lot size system. The average cost CQ of the lot size system is function of control variable Q, where CQ equal to half C1Q plus C3R by Q. And the optimal results we have already obtained, Q star equal to √2 C3R by C1, and the minimum cost C star is equal to √2 C1 C3 into R. Suppose that instead of the optimal lot size Q star, the decision maker uses another lot size which is Q dash, and Q dash is related by the relation Q dash equal to B Q star, where B is greater than 0. Let C dash designate the average total cost of the system then we use the ratio C dash by C star as a measure of sensitivity. It can be shown that C dash by C star equal to 1 plus B square by 2B. This means that the measure of sensitivity is a function of B and is independent of other parameters, that is the C1, C3 and R. Let me define some limitations of EOQ formula. If demand is not known with certainty or demand is not uniform, then obviously EOQ formula cannot be applied. EOQ formula can also be cannot be applied in cases where it is difficult to measure the ordering cost or holding cost, in cases where estimation of demand with accuracy is not possible because of not availability of historic data, for example brand new product, in cases where replenishment rate is not infinite or replenishment time is not 0. Now we proceed to the next model, that is model 1B, EOQ model with different demand rates and no shortage. This inventory system operates on the assumption of model 1A, except that the demand rates are different in different cycles, but order quantity is fixed in each cycle. Let us suppose that there are n cycles over a planning period T, and T1, T2 up to Tn be the lengths of n inventory cycles, and Q be the fixed order quantity in each cycle. Then we have the total period T equal to T1 plus T2 plus ... plus Tn. Suppose that the total demand D is specified over the planning period T. This figure shows the graphical representation of the inventory system, and it could be noticed that there are n cycles and n cycles are of different lengths, whereas the order quantity in each cycle is the same. So, the holding cost will be different for different cycles. The inventory carrying cost or holding cost for the time period T can be obtained as half Q T1 C1 plus half Q T2 C1 plus ... plus half Q Tn C1, which is equal to half C1 QT. The total inventory cost CQ therefore is equal to half C1 QT plus C3 D by Q, and from this we can find the optimal order quantity Q star as Q star equal to root over 2 C3 D by T by C1, and the minimum total inventory cost is C minimum equal to root over 2 C1 C3 into D by T. So, if we compare the optimal results of model 1 and model 1A and model 1B, we observe that the fixed demand rate R in model 1A is replaced by the average demand rate D by T in model 1B. In this model, we have discussed the basics of inventory theory, specifically reasons for carrying inventory, costs associated with inventories, and economic order quantity. We have also developed two economic order quantity models. In first model, we consider the demand rate which is known and constant. In the second model, we have considered the demand rate varies from cycle to cycle. And finally, we compare the optimal results in these two models.